what today's really about is some new notation. So we've got some new notation and summation notation, which I don't think you've really done before, and you're going to get used to it, trust me. We have a little of it, good. Well, what we're talking about today is the a definite integral and thinking about it theoretically in terms of Riemann sums, okay? So there's another way that we can define a function that we can integrate over a specific interval. Now this is from your AB book, so if you want to take a picture of this, feel free. But there's another way to kind of define a definite integral, and then we're going to talk about that today. Here's what we've got going on, okay? If we have some functions that you can integrate over the interval a to b, right? A being the smaller value, b being the larger value. What we can think about is the sum of the area of an infinite number of rectangles underneath the curve. That's what this all is saying, okay? So the limit as n approaches infinity. Well, this notation, this is summation notation. That means for each value, for each number of numbers of things that we have here, so this one comes from 1 to n, we can calculate the area of the rectangle underneath the curve. And so as n, which n is the number of rectangles, as the number of rectangles underneath the curve approaches an infinite number of rectangles, that will equal the actual area under the curve, okay? So this is f of x sub I, right, of that particular rectangle. And I'm going to go into this in way more detail here in a minute. So this is the y value, and then this is the change in x. So, you know, the area of the rectangle is the length times the width. So this is the height, y. This is the change in x, the width. And so I'm just multiplying those together. And then this notation means add all those areas up, okay? The change in x is going to be the difference between a and b divided by however many rectangles there are. And then we'll talk about this in great detail here in a minute. The individual x value that we're talking about is the a, the starting amount, plus however many changes in x we have. Okay, that's what all this says theoretically. Okay, and here is I think, a cool little. Over here we have this interesting looking width of x. Okay, and how to calculate that. So I want to break that down a little bit more to kind of show you what's happening as the number of rectangles gets increasingly smaller, and the width of the rectangles gets increasingly smaller, and the number of rectangles gets increasingly bigger. So in other words, as the width of the rectangle gets smaller and smaller and smaller, and the number of rectangles gets bigger and bigger and bigger, we approach the actual area under the curve. And that's what this is all saying. As the number of rectangles approaches infinity, then the width is going to also change. And then we will get more and more rectangles. And so if you want to take a picture of this, and then I'm going to put a bunch of different descriptors on here so you can see exactly what all this means. Okay, and I discussed it a little bit on the previous slide, but let's really get into it. First off, this is the height of each rectangle. Okay, this is an expression for the height. Now, on this, from where I got this, notice we started talking about k instead of I. Honestly, the way that the AB book had it with I is not common because we already associate that script I with the imaginary number, so it's more likely you'll see a J or a K or something like that. But again, all this means is you have the number of rectangles is going to approach infinity. So this is height, the y value. This, of course, is the width of each rectangle, the change in x for that particular rectangle. Then from there, what we're talking about is the height times the width. That's the area. So this entire expression means the area of each rectangle because it's height times width, or length times width, however you want to think about it, base times height. And so, as you can see by this loop, the width, the x, gets smaller and smaller and smaller because we have more and more and more rectangles. We're dividing that interval up into more and more rectangles, so then that change in x has to get smaller and smaller. And obviously you can see the space underneath the curve that is not counted gets less and less and less, and it gets more and more accurate, right? Okay, this means, again, add all the areas up from the first rectangle to the nth rectangle. That's what this notation means. Have you guys worked with summation notation before or not really?
Yeah.
You have?
I just found it.
Okay, good. That was probably pre-calc though, right?
No.
You did an AB? Good, okay.
It was a problem with
Yeah. And last but not least is we're gonna let the number of rectangles increase to an infinite number of rectangles. That's what the limit is. So the number of rectangles approaches infinity. Remember, n is the number of rectangles. Let's break down this change in x a little bit because on the definition for you, all right? Again, if you want to take a picture of this, feel free. This is obviously a similar representation with only 4 rectangles. And for the ease of trying to understand what that expression means, it's easier to not work with a bazillion rectangles, okay? Now, so there are n rectangles of width change in x, whatever the change in x is. The one thing that has to be true is the change in x has to always be the same per rectangle. The width will always be the same. And the way that we calculate that, again, is we take the end value of x and subtract the beginning value of x and divide it by however many rectangles we have. In general, what we want to say is there's going to be an infinite number of rectangles, okay? And so that's how we kind of come up with each one of these delta x's, change in x's. All right, you take the distance and divvy it up based on the number of rectangles that you have. Okay, and so here's what this, again, a visual of this. So that's b to a, b minus a, that's that distance from here to here, b minus a. And then when I divide by n, that gives me this change in x, since I have however many rectangles that we end up having, okay? Now, another way that we can write this out is like this. So we can replace x sub 1, x sub 2 with all these different expressions, and I'm going to go through where these expressions come from, okay? So essentially what this is saying is if I start here at a, I'm going to add to it 1 change in x to get to the next value. So x sub 1 is our starting point a plus 1 change in x. And let me illustrate this, okay? So when I add, so this is 1 change in x here. A plus, so my a, that's where I started, plus 1 change in x. That's going to be my x sub 1. And I just wrote it up here. Okay. Now we could then say, take this x sub 1 and add another change in x. Well, if I add another change in x, okay, here's what that's going to look like. I've added 2 changes of x from the original value. Here's a change in x, here's another change in x. So that's why my x sub 2 is a plus 2 changes in x. So what we're doing is creating a formula. Later on, we'll talk about a recursive formula. This is what's called an iterative formula. Recursive would be take x sub 1 and just add delta x to it. You take whatever you ended up with and you add another delta x. Well, if I can create a formula using my starting value, then that's going to be more useful to us when we get into using summation notation to express our interval, or our integral. Okay? And then we could keep going like this, right? So if I add another change in x, this value here is going to be a plus 3 changes in x, and so on. Of course, the last one is going to be 4 changes in x. The number of changes in x indicate how many rectangles we're dealing with. So for example, I have 1 change in x here, which means there's 1 rectangle. Here I have 2 rectangles, and I have 2 changes in x, etc. Okay? So here's some more descriptor. The heights, right, the f's, are going to be replaced, these x's, with each of these individual new x's. So this is, again, my starting value, f, so this is the height, f of my starting value plus however many rectangles we have times changes in x. Because when we have 4 rectangles, we have 4 changes in x. When we have 7 rectangles, we have 7 changes in x that are added to my starting value on the interval. Now, here's where it gets even more algebra-y, okay? Since delta x is b minus a over n, we established that at the beginning, this can actually, we can rewrite this change in x as this. Yeah. So we're starting to develop, I'm starting to show you where that formula comes from and why it is that way. And so the area, so this is just the height. So this represents the height of any of the rectangles. Okay, because it's the y. When I take the y times the x, well, this is the x. My formula ends up looking like this. So the kth rectangle has an area of the y times the x. And so when we look at some of these problems, you're gonna have to recognize these are common types of exam multiple choice questions. Another way to represent the integral using summation notation, and I'm going to show you an example of that. And the last thing that we have to say is that we just add all those rectangles up. So that's where the summation notation comes in with this. So after you get that down, I'll go back to the AB example and show you what I mean. Yeah, no, it's not on the AB example. It's going to be on the BC example that I'm going to show you here in a second on the next slide. Just to get us all on the same page. And then I'm going to show you some look-fors when we write these out. Okay, so in summary, what we're talking about here is that the sum of all of these areas of the rectangle will give me the integral, because the number of rectangles is going to approach infinity. We're going to have an infinite number of rectangles to eventually arrive at the actual sum of those rectangles, which will give me the actual area underneath the curve. Now, so let's just break this down a little bit more, okay? So here's where we started. Okay, this was the AB example, the y times the x. We're going to add up all those, that's what this means, add up all the rectangles as the number of rectangles approaches infinity. Now what we have is a way to rewrite this in a different way. Okay, so this is my the f of the starting value plus the number of changes in x times the change in x. Okay, and so this is from your AB book on BC book on page 145. Okay, and so if it feels like I'm over explaining it, it's because this is complicated. There's a lot of abstract algebra here. Now, in our BC book, they flip these two things around, right? So they have the k first and the b minus a over n second. But these are basically the same thing. Okay, and this notation that the book uses is similar to what we've seen as well. Again, our book uses the K, that the AB uses an I. It's not smart. And these are right-hand heights. That's important to note. Okay. Now, what we're going to have to do is write these expressions in this notation. That's what we're going to have to do. And oftentimes on the multiple choice sections, you will see a problem like this and you'll have to pick the right one. Or the other way around. They'll give you this and you have to figure out which integral they're talking about. Okay? So here is our first example. Okay. Now, of course, we know how to find the actual area. But that's not the point of this. The point of this is we're working in theory right now. Okay. Bless you. This is my f of x. Okay, this is my f of x. What is my a value here going to be? 1. Just whatever the smallest number on our interval is. Okay, x is going to get replaced. X is going to get replaced in my f of x. It's going to get replaced in my change of x. And so that's what we have to remember. So remember, our change of x is always the difference of the integration limits divided by n, the number of rectangles that we're going to have. And so what we have to think about is that formula. So a plus change in x, f of a plus change in x times change in x. So here's what that looks like. Okay. I still have my 6, still there's part of the problem. The only thing we're replacing is the x. Okay, and x, in this case, is 8 minus 1 divided by n. I have my limit notation. As the number of rectangles approaches infinity, I go from 1 rectangle to n rectangles. My a value is 1. My change in x is a minus 1 over n times k. So these two expressions should always be the same initially. And of course my squared is still here because that's how we find the y value, 6x squared. We just replaced the x, that's all we did. We just replaced the x. The a plus the change in x times the number of rectangles, or whatever rectangle we're dealing with. And what you will see is this simplified, okay? And it'll look like this. This is, of course, 7 over n times k, and then 7 over n. Usually what happens on those multiple choice questions, okay, there's a couple things you have to look out for. First off, one of your look-fors is, again, the difference of this over n. So seeing a 7 over n should help you believe that response is going to be your answer. However, sometimes there will be multiple responses with this 7 over n. And things that they will do, they'll leave off the 6 as one of the responses. They'll change the summation limits. They'll leave off the squared. They might even multiply this and make it 42 over n. And there's no 6 out here at all. But they are equivalent expressions. So one of the things you're going to have to be aware of when we get to the actual AP exam are those kinds of algebraic manipulations. Okay? In any of those cases, we have to get here before we can get anywhere else. Okay? Does that make sense? Are there questions? Okay, let's look at another one. And this time I want you to try to do it. And don't worry if it's wrong on your first try, but let's try. Again, all we're doing here is changing the way that we're writing x. So in this case, x is going to be a plus the difference divided by n. Okay, so what you should have had, again, you gotta have your limit notation with the summation notation. The natural log's still there like normal, okay? This is my new x, a plus the change. So again, these are both there. All right, and that's what you should have had. Don't leave off the natural log. That's still got to be there because that's how we define our f. Okay, so this is f in summation notation. How many had that? Raise your hand. Okay, very good.